So I am really excited to be here today with Rohit. You're our head cryptographer, and you work with Protier, and I know you work with academics at other institutions. You've invented cool things, and I thought it would be fun for you guys to talk with him and to hear him. And I thought it'd be really interesting to hear about some of the stuff you've invented that we are now putting in TSS. We've heard about TSS. Tell us about it.
Yeah, we can talk more about TSS. It's something we've been working for quite a while, making improvements, finally at a stage where we can say we'll be able to release it in a few months, so it's a pretty exciting time. So yeah, going off where Mark and Nana left off, TSS is our proof system for attesting to a HBAR block. It's basically, in a nutshell, proving that a threshold fraction of an address book has signed off on a given state, which means, and a threshold, you can think of it as, like, let's say half. Half of the address book by weight has signed off on a given state, which means that if there's a subset of adversarial nodes, they cannot forge invalid blocks, and that's a pretty important security guarantee to have. And we're not the first people to study this problem. State signing, a lot of folks have looked at this problem, and oftentimes we find that typically the way they approach it is they would, the participants on the chain, they would publish a set of signatures. And in order to verify whether those signatures are valid, it's your job to look at what is the address book at a certain point in time. And you could typically trace that by looking at block headers, going back in time. And what we feel is ideally, from an end user or from a developer's point of view, it should really be a self-contained proof. We don't really want additional entities like bridges doing this work on behalf of dApp developers. So we really want a self-contained proof. And when you look at this proof, you should be convinced that this is a genuine state signed off by the latest address book on a Hedera or a HBAR network. So if you go deeper, what a TSS proof is proving is two things. One, that a threshold, let's say half of the network address book by weight has signed off on the block. And two, that the address book in question is actually a genuine address book. That it's a descendant of the address book that you had at Genesis. And along the way, you could have several transitions. You could be adding nodes, removing nodes, changing their weights. And regardless of how you got there, you know that this is a genuine address book, and you can trust any proof verified with respect to that. So those two things coming together forms a valid TSS proof. Now, to build TSS, we had to actually come up with a lot of cryptography. We had to invent some stuff. We had to also build on top of stuff that has recently people been working on in the space of snarks, zero-knowledge proofs, threshold, and distributed cryptography. And really what made it challenging is the two things that I spoke about. Supporting weights. A lot of distributed cryptography or threshold crypto systems never really considered the supporting weights when it comes to modeling trust. The other thing is, as I mentioned, the proof here has to be self-verifiable. As in, just looking at the proof with respect to something, a small verification key that we establish at Genesis. And in our case, we have a cryptographic digest at the time of Genesis, which we call a ledger ID. Just using that ledger ID, you should be able to verify any TSS proof at any point in time. Meeting both of these guarantees together turned out to be quite a challenge. and I'll just describe very briefly what entails here. So just before I go on to talk about how we built our TSS, I just want to summarize the requirements that we have. So we want a short proof. In our case, it's 2 to 3 kilobytes, not too large, and we want it to be verifiable against a small cryptographic digest that we established at Genesis called the ledger ID. And any TSS proof has to be verifiable with respect to that. And our ledger ID is something like 256 bits, so not too large again. And it doesn't grow no matter how the network evolves. The two main components in TSS, as Mark and Nana pointed out, is hints and wraps. So I'll just quickly mention what those two are. So hints is a threshold signature scheme. Its job is one thing. It's to prove that a threshold, a half, for example, a half of the address book has signed off on a given state. And it's built on something called threshold signatures. A threshold signature is a cryptographic protocol which allows it's a cryptographic protocol which a set of nodes can participate in, and it outputs a valid signature where at least a threshold number of participants must have participated to create that. That means less than the threshold number of participants, even if they act maliciously, they cannot create an invalid signature. And what makes threshold signatures interesting or non-trivial to build is that they must also be, they must support this feature called aggregation. No matter how large your network is or what your threshold is, your signature has to be a fixed size. And that's what really makes threshold signatures interesting to use and also hard to build. And if you notice, I'm using the term threshold number, because in cryptography, until now, we didn't have a way to support weights when it comes to threshold signing. So hints is the first threshold signing algorithm to support weights natively. It's a protocol that we developed in collaboration with several academic folks as well. It's pretty convenient to use. It produces a fixed signature, about a kilobyte or so. And the signing process is also pretty convenient. Once around, or to sign off every block, every node publishes a small signature that gets aggregated together to produce this aggregate signature that's only a kilobyte in size. Now, the other component here is, how do we trust the fact that this hint signature is valid? Well, the hint signature is verified with respect to an address book, but we have no way of knowing that the address book is safe to trust. And that's where the other proof system, wraps, comes in. TSS contains both the hints and the wraps proof. Wraps' job is to prove that the latest address book is a descendant of the Genesis address book. And the way we do that is, whenever we change our address book, and it could be changing because we're adding or removing nodes, or it could be changing weights, whenever we do that, we have the members of the existing address book sign off on the next address book. So what you have is basically a chain of sets of signatures going all the way back to Genesis. And of course, if you take all of those signatures and you give it to a verifier, that's technically a self-contained proof. If a verifier looks at all of these signatures, that verifier is convinced it's a valid address book. But that's not so convenient. If you recall, our goal is to have fixed size proofs. And that's where we use zero-knowledge proofs. So I'm sure a lot of us here have played with zero-knowledge proofs or snarks, but let me quickly summarize what those are. It's a cryptographic protocol between a prover and a verifier, where a prover takes a computation starting from some state and a set of inputs, and it proves to a verifier that you got to a final state. And this could be any computation. It could be EVM computation, proving that a set of transactions have been applied correctly to state. Or it could be verifying signatures. Verifying signatures is another type of computation. Whatever your computation is, a prover can prove to the verifier that it is a valid computation. In our case, what we can do is we can feed this chain of signatures that I spoke about. A prover can prove to a verifier that there does exist a chain of signatures going back to Genesis. And in our case, a prover would be, let's say, the net consensus nodes constructing the TSS proofs. And the verifier could be a dApp developer or mirror nodes or what have you. So are we done? Well, almost. A verifier is happy. A verifier just looks at a tiny proof. And by the way, in zero-knowledge proofs, we typically have a property called succinctness. That's the S in snarks. That guarantees that a verifier with a tiny amount of work can verify a proof attesting to any length computation. So one would think that we're almost done here, but not quite, because as you can imagine, every day, whenever we rotate our address book, we have more and more signatures. So we can only do this for maybe a handful of days before we really start to struggle. So That's where the proof system in wraps, it makes use of a concept called recursive snarks. Now, think of back to mathematical induction from high school. It works basically the same way. If I gave you a recursive proof for yesterday's address book, and I gave you a set of signatures from yesterday's address book blessing today's address book, the two together should be enough to construct a new recursive proof that is blessing today's address book. And now the prover's job is not growing with time. Every day, or whenever we choose to rotate our address books, all it's doing is taking as input the previous recursive proof and the next set of signatures, and it gets a new proof. And that's how we keep things succinct. That's how we make sure TSS proofs are always a constant size, in our case, 2 to 3 kilobytes. It is always verified with respect to the ledger ID, which is a small 256-bit hash of, and in this case, it's the hash of the Genesis address book. And that's it. Yeah, the two things, the hints and wraps, comes together to form TSS. And yeah, we're excited about it. And of course, we're not done yet. We're now looking at how to make everything post-quantum. But post-quantum transition is a pretty large agenda for us. So I'm going to let Leemon talk more about that.
Yeah, so this is really exciting. We are using a kind of threshold signature that other people don't have. And without that, for a long time, we thought we weren't going to have what you invented. We thought that we were going to have to say we're proof of stake. Each node has an amount of stake that is any number of tiny bars or HBARs, but we have to round it to a number from 1 to 5. That's what we thought for a long time we'd have to do, which is really ugly. It's not exactly proof of stake, it's rounded proof of stake. And you found a way of solving that, and it's totally solved now. Any number of HBARs can be staked, and that is your weight in the voting. And you did it. And in 2018, we said we're going to do state proofs that would have a chain of address books, and the more years our network runs, the bigger your state proofs get. And you crunched it down to a finite size, and it will never change. It's a constant size, no matter how long. I love this. So that's what he's done with that. Post-quantum is also an important thing. Quantum computers are not going to be here this year. The world's experts don't think we're going to have giant quantum computers that can crack cryptography this year. We have them, but we don't think they're going to be big enough to do cryptography, and low enough error rates, and enough logical bits, and all that stuff, qubits, all that stuff. So what we think is that it's going to be years before we have quantum computers that can break cryptography, but there's a good chance that will happen eventually. So a lot of experts say, yeah, maybe 10 years from now we will have a quantum computer that is cryptographically relevant that could break all of our cryptography. That's bad. What about us in Hedera? Can we become post-quantum, be safe against giant quantum computers in less than the 10 years that we have maybe before we're really in danger? And yes. So we do 4 things in our cryptography. We do hashes, we do encryption, we do key agreement, and we do digital signatures. Of the 4 things that we do that are cryptographic, 2 of them are already post-quantum. Our hashes are 384 bits. We are totally secure, as far as all the experts on Earth believe. And our encryption is AES 256. Everyone on Earth thinks that those are secure. Our key agreement, this is how when our computers are talking to each other, the mainnet nodes, they encrypt all the traffic going back and forth, and they have to agree on the key to use to encrypt it. Really, we don't actually need that. We'd be secure even without it. We could just send it in the clear. But it's nice to be able to encrypt it. It's one more layer of security. And for that, we need key agreement. We use TLS. When you go to a secure website, that's what keeps you secret. You go to HTTPS instead of HTTP. You go into a secure website, a little lock appears on your browser or whatever. That is TLS. And we use that between our mainnet nodes when they're talking to each other. And right now, the encryption part of it is fine, but the key agreement part of it could be broken someday when we have big quantum computers. So 10 years from now, maybe that would be broken. Not a big deal, don't really need it for security, but it's kind of nice. And the same thing when somebody submits a transaction to the network. You can do it unencrypted, or you can use TLS, and that would be breakable. Now again, no one's going to steal your money based on it, but maybe it makes front-running easier if someone could break it. So it'd be good to have that be post-quantum. Good news, NIST, this is the government body that does these things, has had a contest for almost 10 years. It started 10 years ago this December, so we're almost up to the 10-year point. And they had a contest where the very top cryptographers all around the world tried to find algorithms that would survive the quantum computer revolution when it comes. And what they did is they finally agreed on algorithms for doing this. They agreed on a way of doing key agreement. ML-Kim. It's called Kyber, like Kyber crystals that make your lightsaber in Star Wars work. And it turns red if you turn to the dark side. That is what they named it. And that is now the standard. And people are putting this into TLS. TLS 1.3 is getting a new version that has this. And people are doing this. Apple just added this in November or December to iOS. For Java, OpenJDK says they're going to roll it out this summer. So this is slowly rolling out. When our libraries support it, we will change that one line of code that turns it on, and then we will have post-quantum key agreement. And our TLS will be post-quantum, and giant quantum computers someday will be unable to break it. And again, we don't really need it for security, but I like the belt and suspenders, the extra layer of security, and maybe it helps you a little bit with front running. We will have that. And I'm expecting that this year. I mean, that's just, as I said, OpenJDK is rolling it out this summer. Apple just rolled it out a couple months ago. I think that the libraries we rely on will have the latest version of TLS sometime this year, and we'll turn it on. Easy to do, no real cost, doesn't slow things down. It's just good across the board. And then there's signatures, digital signatures. This is the big thing. For post-quantum, you need this, because when you do a transaction and you digitally sign, yes, I want to move tokens out of my account, if a big quantum computer could break that, then a big quantum computer could let the attacker steal everything you have. That would be somewhat bad. This is the big threat that every blockchain is worried about, is digital signatures. This is the real danger. We use it internally and externally. Internally, we use this for the hash graph. An event is a node, a mainnet node, creates an event and digitally signs it. And these events form the hash graph. It's what does consensus. You could cheat on consensus if you could forge these signatures. That's bad. And then we use them for our history. The record stream has lists of signatures. And so internally, we rely on signatures that can't be broken, can't be forged. Externally, as I said, every time you sign a transaction to move stuff out of your account, you're digitally signing it. If an attacker could fake your signature, they could steal everything from every account on the whole network, in every blockchain. Those are vulnerable. Right now, in Happy, in the Hedera API or the Hyro API, we have a message called key, capital K-E-Y. This is the key that you put on your account when you create an account. And it can be ED 25519. It can be ECDSA. It can be a smart contract acting like a key. It can be a list of keys that 3 out of 5 are needed to sign, 15 layers deep. We have this list of different keys you can use, and they are not post-quantum. ED 25519 will be broken someday if we ever get giant quantum computers. ECDSA will be broken someday if we ever get giant quantum computers. So 10 years from now, there's a good chance, not necessarily true, but a good chance those will be broken 10 years from now. So we need to fix this. What do? We're going to use one of the ones that won the contest. So Sphinx won the contest, and a digital signature is tens of kilobytes. Yeah, that's the non-starter. Also, dilithium crystals won the contest. Crystals dilithium from Star Trek, using the warp drive. That one won the contest, but it's over 2 kilobytes for the high security signatures. That's really inconvenient. If we had to, we would do it. But Falcon won the contest. It's only 1 kilobyte. Yeah, it's still bad, but it's only half as bad. We'll use Falcon. Now, the Falcon standard hasn't been published yet. It won the contest, but it hasn't been published yet. I expect it to be published any day now. We really thought it'd be by December. They said it'd be done by the end of 2025. When this draft standard is published, we will immediately use it for our internal signing of the events. It's a draft standard. Maybe it's not secure, but we'll just sign it both ways, the new way and the old way. So if you break the new way, who cares? We still have the old way protecting us. And if someday somebody builds a quantum computer, well, the old way is broken, but we have the new way to protect us. So we will do this immediately. It isn't something we have to support forever. If the standard changes by the time it's final, we'll just use it for a little while. And so we will have that. And then a year from now, the final will come out, and we'll just use the final. We won't even do the old signatures. For external, we will change the accounts to allow a new key type of Falcon. As soon as the final one comes out, about a year from now, we will allow that for users. Then we would encourage all of you, if you are building wallets, to nag your users and say, hey, you haven't upgraded to the new keys yet. Push this button and you will upgrade to the new keys. You don't need a new account. It just rotates keys. It's great. And you don't even have to have a new 24 words. You're still protected by your old 24 words. It'll be very painless. So if you are developing software that manages accounts, please do that. The final version should come out a year from now, and we will implement it, and it will be something users can then upgrade. I'm excited about this, and then we'll be completely post-quantum. I wish I could talk to you more. What you're doing is exciting. What you guys are doing is exciting, and I look forward to talking to you in the future. Thank you.